We'll do some homework problems. Starting off with, as we discussed last time, the connection between f and f prime in terms of the functions is important, but also in terms of the graph. The reason why is AP is really fond of giving us these kinds of problems, like 47 and 48 on our tests. So let's take a look at it. 47 from Unit 2 homework says, picture to the right is a graph of f prime. Notice this is the graph of f prime, not the graph of f, meaning it follows the rules of a derivative function, not the original function, which means the intercepts are not the intercepts of f, but the intercepts of f prime, meaning they have different properties. The fact that it's increasing or decreasing, the fact that it's positive or negative, those things are all different because this is a graph of f prime. So take a look at the picture. It asks, what value or values of x does the graph f of x have a relative maximum or minimum? Justify your reasoning. First of all, let's go through some of the definitions we talked about before. When it comes to a maximum or minimum, we define it in two ways. So we can define it by the value of the function, like f of a or f of b. So we can determine a max and min by looking at the values themselves. That's kind of the old way, not the best way according to calculus techniques. Calculus techniques say when f prime is equal to what? 0. That's right. So if we have a picture of f prime, then what we're looking for are our mins and maxes are going to occur in one type of place, where we have zeros. So in this case, there's 3 places where we could have a minimum or maximum. One there, and one there. Now we talked briefly about the first derivative test, and how it allows us to determine minimums and maximums using the derivative rather than using the values itself. So I pose to you that one of these 3 is a max, one of these 3 is a min, the third one could be a max, could be a min, could be something else. Let's use what we talked about before to determine that fact. This first spot. Now, in f prime, it has its own properties because of the picture. But this is asking about what f is doing. So let's analyze what's happening here. To the left of this value, all of our y values are positive. To the right of it, all the values are still positive. So we have a 0 down here at, what is this, -3. To the left of it is positive, to the right of it is positive. To be a min or max, there was a very specific combination we needed. To be a maximum, you wanted to have to the left be positive and to the right be negative. To be a minimum, you wanted the left be negative and the right be positive. This one does not follow either of those rules. So what is it? Well, I mean, I know it's what it is. I can tell what it isn't. It's not a max. It's not a min. So think about the picture of this. I want something that levels off, because that's how derivative of this equals 0, but it's not a max and it's not a min. So think in a picture form in your brain. A picture of something that levels off without having a max or min.
Would it have to be like absolute?
Could be. Could be like that. Which is in fact exactly what's happening here. Notice that in this spot, it's drawn correctly. To the left of it is positive. To the right of it is positive because it's going up on both sides. But there, since it is leveling off, we would assume the derivative is 0. So this is not a max or a min in this particular place. This is neither. Okay. But what about x equals 0 and x equals 2? For each of those, we can apply these rules. X equals 0. It's a max. How do we know that, Michael? Explain for me.
On the left is positive, on the right is negative.
Beautiful. So to the left of 0, we can see it has a positive value in the derivative. So in the original function, it had a positive slope. To the right of 0, has a negative value. So a negative in the prime, in the derivative, means we have a negative slope in the original picture. So that would indicate that this is, in fact, a relative max. Or as we often call it, a local max. What about 2? Min. And explain?
They're negative on the left, positive on the right.
That's right. In the derivative itself, we have a negative on the left, we have a positive on the right. Negative to positive is a minimum. Notice how this is a different feel than when we're looking at the original picture. Because in the original picture, you can just look at it and go, there is very clearly a max because it's the spot where it's the highest. It's right there. Beautiful. In the derivative, we have to analyze it by the values, because the values in a derivative represent slopes. So, going all the way back to the beginning, we can actually answer a bunch of other questions now that we have f prime. We can answer questions about maximums and minimums. Let me ask a different abstract question. In the original function, when is the slope the lowest? The smallest or most negative value?
Just to the right of line.
You're right. So in this spot, which let's just call it, f like 1.1 or something. Cool. At 1.1, this would indicate a place where it has the most negative slope. So on my picture, this would be where the slope is steepest down. What about steepest up?
Excluding like the infinity.
In this case, there wouldn't really be a steepest up that's definable because it goes to infinity on both sides. So we can actually use this to draw a very, very rough picture of what this thing might possibly look like. Let's start by agreeing upon the things we already know, right? We've already said that for this picture, we have a max at 0, we have a min at 2. So, we're now going to attempt to draw a little picture of what we think f could possibly look like. So this is f of x, maybe. Okay, because remember, the derivative can't tell me what the values are. They can tell me the relativity of those values. Are they a maximum? Are they a minimum? Stuff like that. It can't tell you exactly where they are. It can just describe them for you in basic terms. Okay. All right. At 0, I want there to be a max. So I should put it somewhere above a lot of the other rest of the graph. At 2, I want there to be a min. So I should put a minimum somewhere around 2. Again, it's just got to be lower than this one. So I could put it way down here. I could put it even farther down. I could put it right next to it. As long as it's still lower, it's actually still okay. So I'm going to go ahead and throw it, say, right around here. At -3, we're going to have a place where it's going to level off but not change. So it's going to have an increasing, level off, increasing. So over here at -3, increasing, levels off at -3, goes back to increasing. All right. So there's a minimum there. That means it has to come down to there. And to the right of it, it goes back to being increasing. This could be one rough version of this picture, where we have to have a clear leveling off here, a clear leveling off here, a clear leveling off there. This would match, to some degree, everything this problem shows. We have a function with 3 places that are critical values, slopes of zeros, or undefined slopes. Slope of 0, slope of 0, slope of 0. I have a max where I'm supposed to have a max. I have a min where I'm supposed to have a min. To the left of this first critical value is a positive slope everywhere. in between these two is a positive slope in between the critical value of -3 and the critical value of 0. Between 0 and 2, it has a negative slope. From the right of 2, it has a positive slope everywhere. This is a decent representation of what this function could look like. Now, it could be stretched out, it could be compressed, it could, have more curvature or less curvature. Parts of it could stretch up and parts of it stretch down. So, like, just this middle piece could be way up here or way down below. Just this piece over here could be here or farther down. But it's gonna look something like this. And the weird thing is, since we don't actually have any more information, this is as far as we can go. This is it. This is the best we can get. The best possible scenario. This is how you can use f prime to make predictions about the original function. Because f prime tells you a lot about the original function. It tells you how the function is going to act. For those wondering, this would be either a quintic function or probably a septic function, if I had to guess. 48. Same process. You have to be very diligent when looking at your homework starting tomorrow. The homework is not to be posted tonight. This section. We'll have some things that deal with increasing, decreasing, as well as the second derivative and some other little applications we're going to talk about. But for now, you need to be very, very diligent on what you are given. If you're given f and asked to find minimaxes, you have a slightly different process than if you're given f prime. Okay, if you're given g or g prime. Let's keep in mind the standard steps to go through. Ignore the problem. The standard steps to go through to find critical values are: we take a derivative, set it equals 0, start solving. If I already have the derivative, that process changes. I either need to look for zeros for f prime, or if I'm given the equation, I also have to make an adjustment. I have been told this is g prime. G prime of x is equal to x minus 3 squared times x plus 1. Determine on what intervals the graph of g of x is increasing or decreasing. Identify the values or value of x at which g of x has a relative maximum or minimum. Justify your reasoning. Show your work. You're asked to find g prime and determine increasing, decreasing, relative min or relative max. Step 1.
Set equals 0.
Why is that my first step?
Because you already have a derivative.
I already have a derivative. Don't reinvent the wheel here. Don't take another derivative. Because if you take another derivative, you can have g double prime.
3.
So in this case, we take our g prime of x minus 3 squared times x plus 1. We find our solution by setting equal to 0, and then we find, as Ricky says, x equals 3 and x equals -1. So those are my two critical values. If I'm trying to determine intervals of increasing and decreasing, I go now to step 2. I write out my little form, my little number line to create my intervals, and then I start testing them. Let's do it. Number line. On my number line, I need to put -1 and 3. Those are my only two critical values. -1, 3. To determine how the critical values will act, therefore determining increasing, decreasing, min, and max, I need to determine values around them and how they are acting. Because again, -1 and 3 are my zeros, so I got to determine values around them. What values am I going to choose to test these three? -2 sounds great. 0 sounds great. 4 I don't like, but I'll go with it. Well, because y looks like 4. Okay? So what do I need to do with these three numbers that I've chosen to test my intervals? So keep in mind, before I go any farther, I'm going to go ahead and write out my intervals. My intervals are from -infinity to -1, from -1 to 3, from 3 to infinity. I now need to test and see which of these are increasing, which of these are decreasing, and therefore determine maximums or minimums. So what do I need to do with -2, 0, and 4? Determine negatives and positives by doing what?
Testing them in the original function.
No. You do not test them by the original function. You test them by plugging them into the derivative. So take -2, plug it in up here. Take 0, plug it in up here. Take 4, and plug it in up there. And tell me what you get. So -2. That's what I got. So we got a negative there. 0 I got a positive. And then 4, positive. So, let's answer the first piece. On what intervals the graph of g of x is going to be increasing or decreasing? So we've got these 3 intervals, negative infinity to negative 1, negative 1 to 3, 3 to infinity. Which ones are going to be increasing? I of I. Negative 1 to 3? Correct. Do not include 3. Why can we not include 3?
That's where it levels off.
That's where it levels off. It's a critical value. It's a 0. That's why I write these out first, just so I don't forget that. Okay? What are my intervals of decreasing? Negative infinity to negative 1. Alright? Next piece, we've got those 2 done. That's great. I now need to find relative max, relative, I put rev, relative min. So remember, to determine relative max and min, I just need the x value, not the y. Y is required to ask for the value of the maximum, not where the maximum is. Think about it this way. If I ask you where the highest point in the world is, you would say something like Mount Everest. You would not tell me how tall Mount Everest is. Okay, you would list the location, not the value. So, we got negative, positive, positive, relative maximum, relative minimum. What do we know?
The minimum.
What is the minimum?
It is negative 1.
X equals negative 1. How do we know that?
Because it's negative 1 positive.
So we see here in my function, I have negative to the left, positive to the right. That makes this a minimum. Okay, what about 3? Say again? There is no max for this problem. Doesn't exist. Not a relative one anyways. Okay, so let's imagine what this thing could look like. Okay. Here's the information, here's the question. I'm challenging you to take it a step farther. I'm going to go over here. I want to put a little grid up. Like a dad. Close.
Getting better at it.
As I get more practice throughout the year, I get better.
Yeah.
Good. Deserves it.
Fair enough.
Yeah, better. Okay.
Not good enough earlier.
Yeah, I got plenty. Hopefully. The rate I'm going through, maybe not. All right, so at negative 1, something interesting is going to happen. At positive 3, something interesting is going to happen. All right, let's talk about it. So at negative 1, there's a minimum. So I come up here. Let's just throw a minimum somewhere down here. Of course, it could be up there. It just has to be lower than everything else. Okay, to the left of it, it is decreasing. What is that going to look like for that dot? As we're coming down to it. How it goes down could change. So it could be like straight down. That's pretty unlikely. It could be more curved in, or it could be curved out. It could be kind of squiggly, but keep in mind, it's got to still be decreasing the whole time. Okay? So there we go. What's going to happen at positive 3?
Makes sense. It's gonna level off.
It's level off. And what happens in between the two?
Increasing.
So it's going to increase until we get to 3, and then it's going to level off at 3, and then after 3, it's going to increase again. Sure, if you say so. Looks beautiful.
Yes, it's beautiful.
The other cool thing about having the primes is you can actually make some pretty decent guesses at what the original looks like. Because if you look at that picture the derivative has an x minus 3 squared and x minus 1. If I was to FOIL all of that out, multiply it all the way through, I'd end up with a cubic function. If the derivative is a cubic, the original would probably want to be a fourth power of some kind. Does that make sense? If the derivative is a cubic, when we take a derivative, it always reduces complexity down 1. So if it's now a cubic, it had to have been a quartic, or some variation on it. Yes. A big brain. Alright. Let's keep going. This has not been asked with any problem yet, but this is the direction we will eventually go. Because the goal is to learn how to draw functions not using a driving calculator, not using plug and chug, to use calculus to draw accurate, detailed descriptions of a function. It's not as difficult as it seems, especially once you accept these pieces. 49 to 51. Use the graph of the t function, h of x. Oh, graph of t function. I think it's supposed to be the function. H of x, pictured to the right. Use the graph to identify the following. Provide written justification. 49. On what intervals is h prime of x less than 0?
Negative 2 to 0, and 2 to x.
So, this is a graph of h of x. It's a good catch. Those two pieces are correct. From negative 2 to 0 would be one interval that is less than 0. And from 2 to infinity, it would be less than 0. What's another way to ask 49? Let's extend this learning a little bit. What other way can I ask this question? Where is the slope negative? Beautiful. Fantastic. Maybe another way to ask this exact same question. Can you give me one more? Make it just a little bit tougher. Maybe don't use the word slope.
Where the intervals are decreasing.
So I could have the derivative. I could have when the intervals are decreasing. Both those would be fine. You can also say things like when the rate of change is negative. It's another word for slope, right? But those words need to have a firm grasp up here that they're still all connected together. So we could ask about h prime, we could ask about the derivative, we could ask where it's increasing or decreasing, we could ask about the slope or the rate of change. And they're all the same basic question. Okay, 50. I want intervals is h prime of x greater than 0. Negative infinity, negative 2. Union 0 to 2. All right. What did we learn for 49? What's another way to ask 50?
Where is the derivative positive?
Where is the derivative positive?
All the rate of change, like rate of change positive.
Say again?
Rate of change is positive.
Rate of change is positive.
Slope is positive.
Slope is positive.
Interval of increasing.
Interval of increasing. All those are fantastic. Okay? You will often see that for one problem it may ask about the intervals of increasing and decreasing. Next one it could ask about h prime. The problems are asking the same question. Because they're being asked a different way, though, some people look at them and start to freak out a little bit. 51. At what values of x does h prime of x change from positive to negative?
X equals negative 2, x equals 0, x equals 2.
Be careful. From positive to negative.
And then it says from negative. Okay.
So for the first part?
Positive. Would just be x equals negative 2.
X equals negative 2?
And x equals 2. Yeah.
2. So why those two? Talk me through it, Ricky.
On the left of it, it's increasing, so it's positive, and on the right of it, they're decreasing, so they're negative.
Beautiful. That would explain negative 2 and 2. Second part, from negative to positive.
Zero.
So v, x equals 0. All right. Challenge mode. How else could I ask parts of this question? Like what similar things I could get these three answers from? For part A, I could ask for where are the maxims.
Where are the constant? Where's the slope constant?
Not constant.
Constant.
Where the slope is 0.
Okay.
Because the slope can be a constant anywhere.
Right.
A line has a constant slope. That doesn't mean the slope is 0. Okay? For B, you could ask where the minimums are. That's the same thing, right? To the left of it has to be negative, to the right of it has to be positive. So note this phrasing here. This is a phrasing we haven't talked about. I would recommend putting it somewhere in a piece of your notes. Or at least explain what this means in words. So if it asks you a question that says, hey, when does the derivative change from positive to negative? What that means is, if I have a value, a number, on my number line, to the left of it's positive, to the right of it's negative. So it's asking about a max. Another way to describe this exact situation is change from positive to negative. This is where H prime changes from positive to negative. Similarly, I could ask about H prime changing from negative to positive, and it would be asking about a minimum. Thank you, sir. Oh my gosh, it's so empty.
Everything in
So
here.
thankful.
Everything in here is stuff you may want. So.
Beautiful. Amazing. Thank you. Okay. Any questions on 49 and 51? These are different kinds of questions. Notice these questions are not asking you to take a derivative. They're not asking you to set equals 0. They're not asking you to solve anything. They're asking you to understand how the questions are being asked. You have to understand the topic very, very well. If you just know how to take a derivative, you can't answer this question because you don't understand the concept well. Okay? These are the kind of ones that separate people who are good at math from people who are good at calc. People who are good at math can learn how to take a derivative quickly and be able to do that stuff. That's being good at math. Like, I don't want to say it this way. I can teach a freshman how to subtract 1 from the power and multiply that by the power. Like, I could teach them the basic rules and they'd be able to get it pretty quick. I've done it for academic team before. Okay, I taught freshmen the basics of calculus just so they could take a simple derivative. That's usually what they ask for. What I can't teach them is this, because they don't understand this concept yet. They can't get it. And I need you guys to get it. So this is what we need to get the calculus side of this. Okay? It's not just the ability to take a derivative. I trust that you guys can do that. It's the ability to understand it better.
It's going to be very simple how to word it.
Yes, it is a relatively simple problem, but when you word it in a way that doesn't always fit the way we talk about it in class, that does increase the difficulty without actually making it harder. This is where we're going. I would personally not do 52 first. I'd do 53 first.
Oh, yeah. Oh, yeah. Right, you do that.
Yeah, 52 you could do by Algebra 1 techniques, right? Just plug numbers in.
Was it good tomorrow?
Probably do that for a second.
Yeah, those still work. Like, it works great. Just plug in -3, -2, -1, 0, 1, 2, 3, and hope for the best.
Ew.
Or we can use calculus to find the maximum and then use that to work around it. Similar how in Algebra 2 you learned how to find the vertex. And then you can use the vertex to work around it. Well, now we can find the vertex faster and easy. Every time. So I'm going to answer 53 first and then go back and try to do 52. 53 says, find f prime of x. That's easy. What's f prime of x?
Negative x over 4.
Negative x minus 1. How do you get that? Just as a reminder.
We take the x squared to the x squared multiplied by the coefficient of -1/2. So you get negative x. And you take the same with negative x, you take the exponent. Subtract 1 from it, you're showing to 0, so 1. Subtract it.
Beautiful. That was a lot of talking.
Yeah.
It's hard to describe what you're doing when you can do it so easily, right? It's like, it's negative x minus 1. Why are you making this hard?
So much. Why most?
Okay. So, next piece. Find the absolute maximum. It does not say the steps to do this with, which can throw people off sometimes. So I will ask you those steps. How do you find an absolute maximum?
Vertical values.
Vertical values. So what is this problem asking you to do? We already found the derivative. Z equals 0. X equals -1. This is not for certain this is the absolute maximum. I'd have to test around it to verify it is a maximum. So I'll give you that real quick. It's a nice easy function. So I go to -1. I need to test values around -1, so I might select things like -2 and 0. Okay, if I plug in -2, what do I get? Positive. Negative of -2 would be +2, -1 would be 1. One of the positive values, so positive. Plug in 0.
Negative. It's negative.
Remember to plug it into F prime, not the other ones. Since it's switching from positive to negative, that would make this a max. For that, I can answer it in a different way. I know what kind of function this is. Quadratic. It says in the problem it's a quadratic. If it's a quadratic, it has to have an absolute max or an absolute min. So if it has a max, it has an absolute max. Knowing something about the function itself can be very helpful. Alright, now I go back and actually graph this thing. So at -1, there's a max, but that only tells me what the x value is.
So that means we can just plug it into the top function.
There we go. So what is the actual maximum's value? So at -1,
5 halves. The math is off. Today is just not a math day. It's slow.
Here's the question.
I need to find the value of the maximum. I know the x is -1. What's the y?
9.
We're just all over the place.
Am I now? Oh no.
Not
It's like
maximum.
It is 9 that was worth it for me, man. I'm not gonna lie to you. That was worth every second of it.
I subtracted the 1 instead of adding it.
I know, it was great. I greatly enjoyed it. -1 to 9 halves is 4.5. So there's a maximum. Okay, well I've got one dot. How do I make this look like a quadratic? Would you?
Tosh the 1, let's do it.
You know, -1 is 9 halves.
No, y-intercept is 4.
Y-intercept is 4. What's -2 doing?
4.
How do you know what it's for?
It's a quadratic.
It's like an
It's
invisible
like
algorithm, right?
It has a name, axis of symmetry.
Nah.
So if the y-intercept is 4, then next to it has to also be the same value, one unit away. Okay, so now we can just plug in another number, like say 1
2.
or 2. I just gotta plug in another number. You wanna plug in 2?
Plug in 2.
Yeah, sure.
Zero.
It's 0.
So it would be 0. -4.
-4 also have 0. How do you know that, Ricky?
Axis of symmetry.
Yeah, axis of symmetry. Calculus is easy if you remember everything that came before it. Otherwise, you'd be stuck plugging in numbers. You can do it faster if you remember everything, but that's a lot to ask. Okay. So I gotta sketch the graph. When it says sketch an accurate graph, it usually means at least 5 points. There's 3 points you can still mess up a lot. It's pretty hard to mess up. All right. Questions on 52 and 53.
You guys gotta write this down.
Sure. Then in a second, I'm going to ask about 54. You can already see some of what it says. '54 asks, estimate the value of f prime of 0 and explain what the value represents in terms of the graph of f of x. It's another one of those questions where it's asking you to understand the concept more than the math itself. Estimate the value of f prime of 0. So that answers the second piece. Explain what the value represents in terms of the graph of f of x. It's the slope at 0. How do we know it's the slope at 0? Talk me through it, Michael.
Also, slope generating function, so you would input the point or you would input the x value. The x output is the.
Fantastic. When I plug in the point into the slope generating function, it'll always output the slope. So if I plug in 0, I'm getting the slope at 0. Okay, so what is the slope at 0? It asks you to estimate, but we don't actually need to. We have the slope generating function. -1. There is a lot of ways to ask the same basic questions in calculus. Because in other math classes, there are a lot of ways to ask the same question in those basic concepts. I can ask about slope. I can ask about the rate of change. I can ask, how is the function increasing? Or how is the function decreasing? Those are all actually Algebra 1 concepts. But now we can combine that with, okay, well, that's just all a derivative. That all fits into this big overarching umbrella of a derivative. Be sure to note the big difference in this one is what we talked about last time in the table. F of 0 versus f prime of 0. F of 0 would indicate the value at 0, specifically the y-intercept. F prime of 0 is the slope at 0. Questions 52 through 54. Good one. So right, Ricky?
Yeah.
If I was to erase this right now, you'd be pretty upset.
No, you can't.
Oh, dang, that'd be a darn shame.
Oh, but I enjoy it so much.
You're the one time where you actually takes the.
Douglas, I heard something completely different than racist.
Yeah, I heard racist.
There you go.
It has been a weird day.
And it always will.
Yeah.
I don't know, anybody else ever had this weird thing like their tongue doesn't want to cooperate?
That's what's
Yeah.
happening right now.
Yeah.
I think I may for the first time in my life be getting allergies. I've had a stuffy nose for like 2.5 weeks.
Yeah, I don't get a stuffy nose, I get a runny nose. Like, really bad. Especially when I'm asleep. It's,
I guess it's the world getting back at me for always making fun of my allergies.
Oh, how you said that?
I'm not contested.
Where? Oh.
I probably had it though, since I had that really bad flu back in December
Say
last week. Not last week.
Last week, yeah.
yeah.
11 months ago.
Yeah. Now practically like last week.
Okay,
I just
move on.
Last week for this
Isaac
year.
had it.
No.
We've already done these kinds of problems. These are all from last chapter. Finding a tangent line, finding a normal line, that kind of stuff. That's all last chapter. Don't forget those things. They do still exist.
Line.
All from last chapter, all from last chapter. Ah, here we go. Good one to end the day on. Ooh, we got 3 minutes. Okay, we'll get as far as we can. On the interval 0 to 2 pi, find the coordinates of the relative minimums of f of theta is equal to the square root of 3 theta minus 2 sine theta. Let's do it. The problem asks to find the minimums. How do we do that? Critical values. Now, it asks them on the interval, so we don't have to use the test. We can, we don't have to though. Remember, we can also do it using the interval version instead. But before we do any of that, we need f prime of theta to find the critical values. What is f prime of theta?
Square root of 3 minus
2 cosine theta. Now that I've got the derivative, next step, we're trying to find the critical values. Set equals 0. Square root of 3 minus 2 cosine theta equals 0. Next step. Alright. I'm going to shorthand a lot of that. Cosine of theta is equal to square root of 3 over 2. So he says pi over 6.
11 pi over 6.
11 pi over 6. Alright. Now, I could either use this to determine max and mins by testing around it. If you're not comfortable with the trig functions, that's a little tough. Or I could plug in 0 pi over 6, 11 pi over 6, and 2 pi, and see which of those is the biggest, see which of those is the smallest. You'd have to have one of them be the minimum and one of them be the maximum. Because remember, that's the old way, without using the derivative test. So what do you want to do? Do you want to use the derivative test? Do you want to use the old method of integral testing? What do you want to do?
The derivative test.
Derivative test? Okay, let's do it. So, I would need to plug in numbers around pi over 6.
Calculus, man.
11 pi over 6. So I got to plug in one number left of pi over 6, in between pi over 6 and 11 pi over 6, and right of pi over 6. I'm going to pick these ones the first time to move this along a little bit. 0, pi,
2 pi.
2 pi. You better believe it. Okay? Let's plug them in and see if we get positive or negative values. So it's helpful to have the unit circle memorized here. If I plug in 0, plugging in 0, cosine of 0 is 1. Square root of 3 minus 2 times 1. 2 times 1 is, of course, 2. Square root of 3 minus 2. Even if you don't know the square root of 3, there's a way to do this. If I have something like the square root of 3 minus 2, all I care about is if it's positive or negative, right?
Right.
What if I put these in the same form? It would be easier. Usually we think of putting them all in decimal forms. So what if I put them all in square root form? So the square root of 3 minus square root of 4. Which is bigger? The square root of 4 is bigger?
Yeah.
It's bigger number. So if I subtract it, it's going to be negative. That's a little trick you can use. Just let you know. Okay. Plugging in pi. Cosine of pi, unit circle, cosine of pi would be negative 1. So I'd have square root of 3 minus 2 times negative 1. Negative 2 times negative 1 would be positive 2. Square root of 3 plus 2. I hope you all know that's positive. And then 2 pi should have the same solution as 0 because they're the same spot in the unit circle. So it should also be negative.
So minimum at pi over 6.
So minimum at x equals pi over 6. How do you know that, Ricky?
Because it's negative on the left of pi over 6 and positive to the right.
Correct. Negative to the left, positive on the right. Where would be the maximum?
11 pi over 6.
11 pi over 6. We're going to stop the recording. Hope you guys have a good day today. Not too much fun.